Here's another example problem in the study of work and kinetic energy, and also an investigation of ideal springs and Hooke's law. This one was taken from the AP Level C exam in the year 1988. So we're told that there's a 5 kilogram object sliding with a speed of v0 in a hollow frictionless pipe. We can see that 5 kilogram object here with the initial speed. The end of the pipe contains 2 springs, right? 1, 2, an inner and an outer spring. And we're going to assume they're ideal, so that they're governed by Hooke's law. Okay. One spring is nested inside the other as shown. The 5 kilogram object makes contact with the inner spring at point A. There's point A. And then it moves 10 centimeters before it makes contact with the outer spring at point B. So it goes 10 centimeters and then makes contact with the outer spring at B. And then it moves an additional 5 centimeters before ultimately coming to rest. Okay, so we can see all that in the diagram. Then there's a graph that shows the magnitude of the force as a function of the displacement. So we have force graphed on the y-axis and distance graphed on the x-axis. Well, Hooke's law tells us that the force exerted by a spring is negative the spring stiffness, which is symbolized by the letter K, times the elongation of the spring or compression of the spring. It works in both directions. If we're just interested in the magnitude of the force, then we get rid of the negative sign, say it's equal to K delta X. Now we can say K delta X plus 0, so now this looks like Y equals MX plus B. Now why would we do that? Well, because we're putting on the y-axis the magnitude of the force. The magnitude of the force is graphed on the y-axis. And on the x-axis is the distance or displacement. So the slope of the graph is the K value of the spring. So to get our answer to question A, calculate the spring constant, in other words, calculate the K value, we just need to find a slope. Rise over run. So if we look from A up to point B, when that inner spring is engaging, we have a rise of 20 and a run of 0.1. So this couldn't be any easier. The K value is equal to 20 newtons divided by 0.1 meters. Now notice that the spring didn't actually compress a full meter, but that's how we always express the K value. If we multiply numerator and denominator by 10, we could say this is the same ratio of 200 newtons to compress it 1 meter. So if the spring remained ideal over that much of a compression, then it would have a K value of 200 newtons per meter. Part B is to calculate the decrease in kinetic energy as it moves from point A to point B. Well, a decrease in kinetic energy is a change in kinetic energy, and the work kinetic energy theorem tells us that work and change in kinetic energy are equal to one another, but we also know that work can be found by taking the area under a curve. So all we need to do is find out what's the area of this shaded portion of the graph. That's a triangle, 1/2 base times height. So 1/2 times 0.1 meter times 20 newtons. That's equal to 0.1 times 10. It's equal to 1 newton meter. But a newton meter is the same thing as a joule. Okay, so the decrease in kinetic energy as it moves from point A to point B is 1 joule. Part C, calculate the additional decrease in kinetic energy as it moves from point B to point C. So in the same way, we're going to get the answer by calculating an area. So we already accounted for 1 joule of work. Let's calculate the additional work done. So we need to calculate area. Well, let's do this. Instead of finding the area of this shape, let's divide it up into a triangle and a rectangle. So we need to find the area of that shaded region and the area of this shaded region. Okay, let's do the easy one first. The rectangle, that's just length times width. So we have a width of 20 newtons and a length of 0.05 meters. 20 times 0.05, oh, that also gives us 1. Okay, so that's 1 joule. And then this triangle, let's see, it's got a height 60 to 20. Okay, that's a height of 40 newtons, and it also has a base of 0.05. So 1/2 times 0.05 times 40, that also comes out to be 1 joule. So the total work done as the object moved from point A to point C is 3 joules, but the additional work past point B is equal to 2 joules. So that's our answer to part C. Calculate the additional decrease in kinetic energy, 2 joules. Part D, calculate the initial speed of the object. So the net amount of work is a 1 joule from A to B plus the 2 joules from B to C to give us a total of 3 joules. That work is change in kinetic energy, which is final minus initial. But the final kinetic energy at point C is 0 because it comes to rest. So the work is equal to negative the initial kinetic energy, or negative 1/2 mv initial squared. But we're really just interested in the magnitude here, right? I suppose the work itself is negative because the displacement, delta S, is to the right, but the force exerted by the springs is back to the left. So these negatives cancel one another out. And we can do some algebra to solve for the initial velocity. Say it's 2 times the work, square root of 2 times the work divided by the mass. So the initial velocity is equal to the square root of 2 times 3 joules divided by 5 kilograms. Now I'll leave it up to you to prove dimensionally that the square root of a joule per kilogram is indeed a meter per second. In any case, this is the square root of 6 joules over 5 kilograms. So that's the square root of 1.2, which comes out to be about 1.1. Initial velocity, 1.1 meters per second. Part E, calculate the spring constant of the outer spring. So we know this inner spring has a K, we'll call it K inner, is equal to 200 newtons per meter. We have to find the value of K outer. Now you might think, well, wait a minute, the way we found this 200 was we found the slope of this line segment. So can't we find the K value of the outer spring by getting the slope of this line segment? Not quite, because the slope of that second line segment is actually an expression of the combined effect of the 2 springs acting together from point B to point C. So we need to take another approach to it. For part E, in order to find the K value of the outer spring, we're going to say that the work from point A to B, from point A to C, which we know to be equal to 3 joules, comes in 2 parts. It's the work done by the inner spring plus the work done by the outer spring. But the work done by the inner spring should be calculated as the integral of the force of the inner spring dot product. I was going to say ds, but because the springs are compressing along the x-axis, I'll call it dx, plus integral of F outer dx. But because these are ideal springs and they're governed by Hooke's law, we can replace the force with kx. So k inner x dx plus the integral of k outer x dx. So this means the net amount of work is equal to, let's see, what's the solution to this integral? 1/2 kx squared. So 1/2 k inner delta x squared, and k inner, or the inner spring, is doing work all the way from point A up to point C. So the delta x here, we're going to call delta x AC, plus 1/2 k outer delta x squared, just doing integration, thinking of integration as the antiderivative. But the outer spring isn't doing work from point A all the way to point C. It just does work from B to C, right? So this is delta x BC. Okay. We're trying to solve for k outer. Let's see, so we'll multiply both sides of the equation by 2. K outer times delta x BC squared is equal to 2 times the net amount of work minus k inner times delta x AC quantity squared. Okay, so I guess we need to divide by delta x BC. So k outer is 2 times the net amount of work minus k inner delta x AC quantity squared, all divided by delta x BC quantity squared. And now that we've done all the algebra we can, we just need to plug in numerical values, and the k value we're looking for is 2 times 3 joules minus 200 newtons per meter times 0.15 meters quantity squared, all divided by 0.05 meters quantity squared, right? The distance from A to C is 15 centimeters, but the distance from B to C is only 5 centimeters. So our k value is equal to 6 minus, let's see, grab a calculator, see if you get the same values I get. Six minus 4.5, all divided by 0.0025. Which comes out to 600. Oh, wait a minute, I cheated this. Let's see, these meters get squared. So a Newton per meter multiplied by a square meter would be a Newton meter. That's a joule. So we've got joules combined with joules. And then divided by, so our numerator is joules, our denominator is square meters, but a joule is a Newton meter. So a Newton meter per square meter is a Newton per meter. Oh yeah, of course. We're trying to find a k value after all. So there we have it. Now notice what we would have got had we calculated the slope of the other line segment. Let's see. Rise over run. So this is a rise that goes from 20 up to 60. So it's a rise of 40 newtons and a run of 0.05 meters. So that would have given us, let's see, 40 divided by 0.05, that would have given us 800 newtons per meter. But we can see the correct answer is 600 newtons per meter. But you notice something? If we were to take the inner spring's constant and add it to the outer spring, that would be 200 plus 600, which would give us 800 newtons per meter, which was the slope of that other line segment. So see, like I was saying, the slope of this line segment here was determined by the combined effect of the two springs, which is found by adding 200 plus 600. So it seems like everything checks out in the end. Wonderful. Thanks for watching.